EC 201, lecture 19. Alright, so the last time around we derived from scratch what is commonly called the common drain amplifier, and the common drain amplifier comes about due to our quest of trying to build an incremental voltage controlled voltage source, and in that endeavor we are successful in building an incremental voltage controlled voltage source of gain 1 and a schematic which realizes the common drain structure is the following. What do we call the bias current? IRF. This is an infinite capacitor. There was RL. This is Vs. So this was the schematic of the common drain amplifier that we derived in the last class. The quiescent current through the transistor is stabilized to be equal to IRF irrespective of the threshold voltage of the device. What we saw was if the GM of the transistor tends to infinity, then Vout by Vs tends to 1. By the same token, we also saw that the output impedance of the amplifier of the voltage controlled voltage source, Zout tends to 0 as GM tends to infinity. In other words, when the GM becomes infinite, this behaves like an ideal voltage controlled voltage source with a gain being equal to 1, also called the source follower. The terminology is quite similar to that used when you build an op-amp based unity gain amplifier. The output follows the input, just like how the op-amp based unity gain amplifier is called the voltage follower. The source, the incremental signal at the source follows the incremental signal at the gate. And we derived expressions for the gain and the input impedance and output impedance when the GM is finite. And the bottom line is that in practice we cannot make GM infinity, but if we make GM sufficiently large, where large is defined as GM being much larger than 1 by RL, then this kind of begins to approximate an ideal GM. A GM tending to infinity. So the small signal properties of this amplifier have all been figured out. The next thing to do is to figure out the large signal properties. So what do we do? What are we trying to do now? When I say large signal, what do I mean? I know that the incremental gain is 1, so I put in a small sine wave, I get out a small sine wave. I put in a slightly larger sine wave, I get out a slightly larger sine wave. Obviously, the good times must end sometime, right? So if I put 100 volts into the poor amplifier, obviously the output, something bad must happen to the output. And based on your experience with the common source amplifier, what do you think will happen? As the input signal goes on amplitude of the input sine wave goes on increasing, we have basically come to expect that the transistor M1 goes out of saturation, and the moment the transistor goes out of saturation, none of these things are valid anymore, because now you suddenly have the GM falls down dramatically and the output impedance, which was infinite before or very large before, now becomes very small. And the moment the transistor goes out of the saturation region, the incremental gain will decrease dramatically, which means that the output, which was supposed to be a nice clean sine wave, now has presumably the top or the bottom chopped off. Our job next is to figure out what is the maximum amplitude of the sine wave you can put into this amplifier before crazy things start happening at the output. Does that make sense? So how do we proceed? How do I go and figure out the amplitude of the largest sine wave I can put in before the transistor gets out of saturation? We have done this with the common source. Okay, so we know that the transistor will get out of saturation if the drain goes 1 VT below the gate. But here the drain is not going anywhere. It's sitting at VDD. So the moment the gate goes one threshold above the drain, the transistor will get triode. That's bad. We know that. Okay. On the other extreme, what happens? The drain current of the transistor could go to 0, in which case the transistor is cut off, and that's bad too. So we have to figure out gate drain voltage as a function of time. And why is it varying as a function of time? Because the input is varying in a sinusoidal fashion. And we need to find the total current in the transistor. To figure out the limit for triode operation, we are interested in the gate drain potential. To figure out the limit for cutoff, we are interested in the total current or the drain current of the transistor. Okay. In either case, for the limits of large signal operation, we are interested in the total voltages and total currents through the MOS transistor. Let's first try and figure out the limit for cutoff. If Vs is Va sine omega t, and for cutoff of the transistor, we are interested in finding the drain current. How do I find the total drain current? Is the quiescent current plus the incremental current. The quiescent current is quite straightforward. What is the quiescent current? It's simply IRF. What about the incremental current? What is the incremental equivalent circuit? The incremental equivalent circuit is, what happens to VDD? Ground. What happens to the current source? Open. The capacitor? Short. So this is RL. This voltage, so this simply becomes Vs. Okay. What do you think? Assume the output impedance of the transistor, that is the RO of the transistor, is infinity. So what did we, if the transconductance is Gm, what is the incremental output voltage V out? The incremental output voltage is Gm RL by 1 plus Gm RL times Vs. So what is the incremental current through the transistor? Just look at the circuit and it's obvious. What is it? The incremental current flowing in through RL also has to flow through the transistor. The incremental current at the output, which is simply V out by RL, also happens to be the incremental current to the transistor. But the output voltage is Gm RL by 1 plus Gm RL times Vs, which is Va sine omega t. This is the total drain current to the transistor. Oh, sorry, that's true. Divided by RL. What is the limit for cutoff? How would I figure out now the limit for cutoff? When the total current, drain current in the transistor goes to 0, that's when the transistor is off. What does that mean? That means, so this will go to 0 when at omega t equal to pi, and the value of Va will be Iref times RL times 1 plus 1 over Gm. This is just solving this equation, that's all. So this is the limit for cutoff. When the transistor goes into cutoff, is the output lower than the quiescent value or higher than the quiescent value? It is lower than the quiescent value, and that's please note that this cutoff will occur when omega t is equal to minus pi by 2, okay, or 3 pi by 2. So that happens at the lowest point on the negative half cycle. Okay, that's when the device is pushed into cutoff. That makes sense? What is the limit for saturation? The limit for saturation is when Vg becomes equal to Vd plus Vt, or Vd becomes Vg minus Vt, both are equivalent statements. The absolute potential of the drain is fixed and is equal to Vdd. Okay, this is Vt. What is Vg? The quiescent value plus the incremental value. What is the quiescent value at the gate? It's Vdd times Rb by Ra plus Rb. Very good. Plus Va sine omega, which means Va is Vdd times Ra by Ra plus Rb plus Vt. So the MOS transistor is getting into the triode region when the input voltage is going up or down? Going up. So does this, is this the same thing that happened in the common source amplifier, or think carefully. In the common source amplifier, when the gate moved up, was the transistor going into triode or saturation? Here also it goes into triode. The limit for saturation happens to be Vdd times Ra by Ra plus Rb times plus Vt. From the expression, we see that this limit, the amplitude you can put in before the transistor saturates, becomes larger as Ra becomes large. Okay, if Ra increases, Vdd times Ra by Ra plus Rb will increase, thereby pushing up this Va here. Intuitively, why do you think that makes sense looking at the circuit diagram? Looking at this circuit diagram, I say, I knew this already. Why? If Ra increases, why do you think the limit? So, if Ra increases, this potential will increase or decrease? Decrease. Okay. So, if the quiescent value at the gate decreases, that means it will take a larger input signal to push this node over and above Vdd by one threshold. You understand? The moment this node goes one threshold above Vdd, the transistor goes into triode. If this was the gate potential was inherently lower to begin with, it means that you can put in a larger amplitude sine wave before the transistor gets pushed into the triode. Very straightforward. So if I call the limit due to cutoff Va1 and the limit due to saturation Va2, what is the amplitude of the largest sine wave I can put in before the output becomes clipped? Very good. So the largest amplitude is the minimum of Va1, Va2. That finishes the discussion on the common drain amplifier. You can see that we spent a lot of time on the common source, and the same principles are applicable to the common drain. Finding strings and all that. It's the same old procedure, and you will see that this is the same old thing for any complicated circuit that you see. You find the quiescent operating point, you find the incremental circuit, you find the total drain currents and the drain gate voltages, and you'll be able to very easily figure out what the maximum amplitude is before distortion sets in. Okay. So, in other words, we've seen how we take the basic transistor, which we know now to be, this is an incremental voltage controlled current source, and in principle there is no limit to the amount of GM you can get. Using this, we derived the common drain amplifier, which was a way in which you can get a voltage controlled voltage source. It makes sense to now figure out all the other 3 controlled sources. So this is the incremental model for the basic MOSFET. The next thing is to try a voltage controlled current source. And it's understood that we're trying to realize an incremental voltage controlled current source. So what do? How would I go about tackling this problem? If I want a voltage controlled current source, I need something where I out is V in by some R. V in is the input voltage, I out is the output current, and what is the input impedance of an ideal voltage controlled current source? Infinity. What is the output impedance of an ideal voltage controlled current source? Also infinity. Okay. So fine. So before we start putting down transistors and getting excited, let us actually sit down and think. You were in the lab, I gave you a voltage source, and I said, hey, give me a current source which is V in by R. What will you do? What all will you want from me before you can do that? What you will do is, you say, hey, give me a variable current source. I can't presumably produce current out of thin air, right? So, give me a variable current source, which I will denote like this, and here is your input voltage. What will you do? You can't compare current with voltage. What you will do is the following, which is, you know that you have this gadget at the back of your mind, you know that you can compare voltages, because the MOSFET is a gadget that can produce a large current in response to the difference between 2 voltages. And when we say comparison, it means taking the difference. So it makes sense so you have a variable current source. I pass this through a resistor R and compare this voltage and this voltage. This voltage, if I call this X, if I call this Y, so if Vx is greater than Vy, what does it mean? I is 2, which means that I must increase I. Common sense. Similarly, by the same token, if Vx is smaller than Vy, it means that I is too high, must therefore decrease I. In other words, the variable current source here must be controlled by the difference between the node potentials at X and Y. In other words, I must be dependent on Vx minus Vy. Should it be dependent on plus Vx minus Vy or minus Vx minus Vy? Plus y. If Vy is too small, then I must increase I. So this is indeed correct. I must be proportional to Vx minus Vy. If I is proportional to voltage, it must be equal to something of the form Gm times Vx minus Vy. And what you need in practice, I mean, if you want to make Vx is equal to Vy, it's only if Vx is equal to Vy will I be equal to V in by R. Okay. So in other words, this Gm must be, the Gm must be infinity. Okay. In other words, you must be extremely sensitive to the value. I mean, you should be prepared to turn the knob of the variable current source even if you notice a minute change difference between Vx and Vy. As I said again, this is like the tough policeman who makes sure that people comply with the law. The only way in which this can happen is if Gm tends to infinity. Does that make sense? Replace this by Gm times Vx. And intuitively, how does this work? This is x, this is y, this is plus, minus. So the moment this controlled source sees a small difference between Vx and Vy, it pumps current in the right direction in an attempt to make Vx equal to Vy. So this is negative feedback. Can you identify the transistor? Oh, by the way, which is the output you want? You wanted a voltage controlled current source. Where is the output? This current, not through the resistor. This is your I out. Why can't I take the output to the resistor? If I try and fool around with the current in the resistor, the moment I load it, the current will change because some of the current will flow in through the load. So it makes sense to actually take this current. This is a current source anyway. So it makes sense to tap that current as the desired output. So now can you identify the transistor? So which is the transistor? Please note that the transistor is a voltage controlled current source, and here you have a voltage controlled current source. These terminals correspond to the transistor. So X corresponds to the gate of the transistor, Y corresponds to the gate source, and Z corresponds to the drain. So, and this is the incremental input. This here represents the incremental circuit of a voltage controlled current source, where the incremental output current I out is given by the input incremental voltage divided by R. If Gm is, does anybody see a similarity between this and the common drain? The same thing, except that in the common drain, the output is taken at the source. Here we are tapping the current through the transistor. This is often called the admittance amplifier, or the transconductance amplifier. what you did as far as biasing is concerned with the common drain, you can do the same thing with the transadmittance amplifier. Also, let me just quickly give an example. This is just one way of doing it. If Gm tends to infinity, the incremental current is going to be Vs by R. If Gm is very large but doesn't tend to infinity, what do you think will be the current? This is nothing but the common drain. If I looked at the incremental output voltage here, for a finite Gm, what was the output voltage? Vs times Gm R by 1 plus Gm R. So what is the incremental current to the transistor? We calculated this just now. It's nothing but V out by R. So you can see that as Gm tends to infinity, GMR will tend to infinity, which will make this factor tend to 1, which will make the incremental drain current equal to Vs by R, as we had expected. And another important point is to note that if the Gm is large, it doesn't matter how large it is, the transfer function of this amplifier is independent of the Gm. Pardon? Business opportunity. Well, okay. Now, where have we seen this? This is a characteristic of negative feedback systems where, do you all understand that there is negative feedback here? Okay. That's how in fact we derived it. We take I times R, we compare it with V in and go and tweak the current until I out times R becomes equal to V in. And we saw that when you have a negative feedback system, the closed loop performance is independent of the forward amplifier as long as the gain of the forward amplifier is sufficiently large. If the Gm is sufficiently large, it basically means that the transistor doesn't tolerate any nonsense. The moment the incremental source voltage is even slightly different from the incremental gate voltage, it goes and kicks the resistor so hard that the output voltage better become equal to the input voltage. So this gives you a way of implementing a voltage controlled current source where the properties of the voltage controlled current source are independent of the device itself, which is a very good thing because the Gm of the device can vary all over the place. But as long as it's sufficiently large, we see that the transconductance or the incremental output current by the incremental input voltage is very nearly equal to 1 over R. And whenever you see things like this, you can be quite sure that there is a negative feedback loop hidden somewhere doing a very common circuit. Put a resistor R here and look at the incremental output voltage V1. So can somebody venture and tell me what the incremental output voltage V1 will be? What can you say about the incremental voltage here versus the incremental voltage here? They are the same because we have the infinite capacitor. Great. Okay. Okay, when you are in doubt, what do you do? Draw the incremental equivalent. Okay. This is R. This is Vs. Okay, what is the incremental equivalent at the drain? R to ground. Okay, this is V1. So if Gm tends to infinity or Gm is very large, what is the incremental current in the transistor, drain current in the transistor? It's Vs by R. That current flows which way in the resistor? Up or down? It flows up. So what is the drop across the resistor? The voltage drop across the resistor in this direction shown is, so V1 becomes equal to minus Vs. the voltage here for large GM, V2 is approximately equal to Vs. So you can see that this circuit is capable of taking a sine wave and giving you both the phases of the sine wave. Okay, one which is 180 degrees one which is in phase and one which is 180 degrees out of phase. So this circuit is often called the phase splitter. So you should be able to now very easily calculate the largest sine wave you will be able to put in before the transistor gets into saturation or cutoff. I don't see any point in doing it. It's the same old thing. Just please do this at leisure. The next thing to do is the third thing, which is the current controlled current source. So in other words, we want to build an ideal incremental current controlled current source. And what are the attributes of an ideal current controlled current source? Zin is 0 and Zout is infinite. Okay, let's try and derive the circuit. What would you do? You are in a lab, I gave you one current, I wanted you to produce a current which is the same current. Let's take the current gain to be 1 for simplicity. So in other words, I want I out, the incremental current I out, to be exactly equal to the incremental input current I. So if I gave you a current source and said, hey man, produce me another current source with the same value, what would you do? Okay, so one thing is to say, if I had a variable current source, I would say I compare the value of this variable current source with my input current. Okay, and then if I look at the potential of this node, if Vx is increasing, it means that I out is too high. I must reduce I out. On the other hand, if Vx is decreasing, it means I out is too low. I must increase I out. If I compare Vx, the incremental value at the voltage at this node Vx, okay, to what value? To ground. And please note these are all incremental circuits. In an incremental circuit, you cannot have a DC voltage. Okay, so I compare it with ground and kick I out up if Vx is too low. If Vx is too high, then I reduce I out. In other words, the variable current source is a current source which is controlled by the difference between the potential at this node and the potential at Vx. In other words, I out must be proportional to, is it 0 minus Vx or Vx minus 0? Why is it 0 minus Vx? If Vx is negative, I out must be positive. If Vx is negative, it means that the I out is too low, so I have to increase I out. So if Vx is negative, I out must be positive. So in other words, it must be, I out must be proportional to, must be equal to some Gm times 0 minus Vx. And as usual, what should happen to Gm? If you want perfect compliance between I out and I in, if I out exactly has to be equal to I in, then Vx better be equal to, okay. So the moment there is even a small difference between I out and I in, this control source must be so strong that even a minute difference between the two voltages Vx and ground must result in a massive correction of V out, of I out, thereby bringing I out back to I in. In principle, this must be as large as possible or equal to infinity. So now can somebody identify the transistor? This is some Gm times 0 minus Vx. The gate is grounded, very good. The current source occurs between the drain and the source. So this is the drain, this is the source, and this is the gate. So this represents the incremental circuit diagram of what we are after. Where is your output? The incremental current through the drain is the current that you are after. Does it make sense? Okay. This is the incremental circuit, so we need to do the, so can somebody help me with the bias? Okay, RA, RB, somebody says. We need to bias the transistor and saturation. So this is VDD. The drain is grounded. This is RA. This is RB. The gate must be grounded. So what should I do? Put an infinite capacitor between gate and ground. This is IREF. And this is VDD, alright. So somebody suggests a capacitor and then a current source, an incremental current source IN. But then I realized that if I had a current source of IN, anything in series with the current source hardly matters, so I can remove the capacitor and inject current right away. Incremental output is the output current. Okay. So what would be the incremental output current by the incremental input current? When you are in doubt, draw the incremental equivalent circuit. If you draw the incremental equivalent circuit, you end up with this chap, the direction of IN. Yeah, okay. Fine. Alright. So what is the ratio of incremental output current to incremental input current? Must be 1. Does this depend on Gm? What is the current flowing through the gate? 0. Okay. So whatever you pull out must come from the drain. So I out by IN is identically equal to 1 regardless of the Gm. What is the input impedance? Looking in here incrementally, we have already done this. Does this look familiar, people? This incremental diagram here, does it look familiar? I am doing the same thing over and over and over again, and I've been successful in conning you all into thinking they're all different. This is again the common drain, okay, except that RL tends to infinity, the Vs is 0. In the common drain circuit, if you go and put Vs to be equal to 0, okay, and RL tending to infinity, you basically get the same circuit diagram, okay, which means that the output impedance of the common drain, the expression that you derived there, is also the input impedance of this current controlled current source is if Gm tends to infinity, the output impedance of a common drain amplifier is 0, which by the argument I just made is also the input impedance of this amplifier. So the input impedance of this current controlled current source is 0 if Gm tends to infinity. Another way of looking at it is that if Gm tends to infinity, then for a finite value of I out, what must be the difference between these two nodes? Okay, so this is Gm times the potential of this node, which is 0, minus Vx, okay. So if Gm tends to infinity, if this current is finite, then the difference between these two nodes must be 0, which means that Vx must be 0. So as far as the input current source is concerned, the node that the potential across it is always equal to 0 regardless of how high the current is, which by definition is a short circuit, which is equivalent to saying that the input impedance of the current controlled current source becomes equal to 0 if Gm tends to infinity. Does that make sense? In practice, again, if Gm is finite, the input impedance will become 1 over Gm, and clearly Zn tends to 0 if Gm tends to infinity. What do you think the output impedance is? What is the output impedance? Okay, you don't know, how will you find out? You draw the incremental equivalent circuit. For the transistor, the incremental equivalent circuit at this part here is simply a current source. Since that's a current source, obviously the impedance looking in here is got to be infinite. So in this amplifier, we see that the gate is grounded and the gate terminal is common to both the input circuit and the output circuit. Here you also see that the drain is grounded, but that's beside the point. What is usually done in practice is to put a load resistance here and convert this current into a voltage. It's not necessary that the drain be incrementally grounded, but it is necessary that the gate be incrementally grounded, because we are comparing the drain current with the input current by connecting them in a way that they fight each other, and compare that node potential to ground. So it is important that the gate be grounded. So this amplifier, by the same token, so far, this is called the grounded gate amplifier, or the common gate amplifier, and this is an incremental current controlled current source. So tomorrow we will see the aspects related to